Hello and welcome. In this video, we are going to look at this high pass filter. This is an RL circuit, and we expect inductors to allow low frequencies, low F, to pass down through them. And any high frequencies, we're actually going to tap into the circuit right here, and we're going to pull them off, and we're going to send them like through a speaker, right? And that's going to have audio output to it. And we don't want, low pitch humming or fan noises, something like that on it. And so that low frequency is going to drop through the inductor, and any high frequency, like audio from voices, that kind of stuff, is going to go through the top. And originally, you'll hear like older DJs on the radios have to talk in this really, really high pitched voice to make sure that their voices hit that high frequency mark and don't get filtered out by low frequency inductance circuits. And so these are reactive, right? They're going to react to whatever input we put into them, like audio. In this case, we're just going to use a switch. And so if we grab out our oscilloscope, we can kind of see what this inductor is going to do. But let's check our time constant first, right? Because our time constant is going to tell us how fast we actually need to switch this switch to make a reaction time. And so we can say that that is our P value, and that's going to be our inductor divided by our resistor. And so in this case, 150 micro. We'll put that in, open parenthesis there, and say 150 times 10 to the negative 6. And we'll close that and divide that by what we know our resistor is, which is 2200. And so we get, we'll move that over as well, we'll get a factor for our time constant equal to 68.2. And we moved it to the negative 9, so that's nanoseconds. Right? This is in seconds. And so that's how long it takes for our inductor to start to respond. So for me to flip this switch in that length of time is going to be extremely challenging, but we can see something else with this switch in the circuit here. So if we grab our oscilloscope out, that's the fourth one down on the side here, or you can go to your Simulate tab, Instruments, Oscilloscope. You want to use this oscilloscope and not the 4-channel one because it's going to be a little bit more challenging with the 4-channel one. We'll pull this oscilloscope out and set it off to the side here. Our A probe lines here, we want positive and negative. We want to wrap that around our source, and that source is actually going to be both our switch and our voltage here. And so the positive side of this A channel can go at the beginning of our switch, and then the negative side goes to ground, any ground, even this one down here. Right? All grounds are going to be the same value. We could even make those two the same ground if we wanted to. Okay, and then the positive side of our B channel needs to go around our resistor, and so we can make that go all the way over here to the front side of our resistor, and then the negative side to the back side of our resistor. Right? And to tell these two signals apart, we want to change one color. We want to change the segment color of channel B by right-clicking on it, and then picking any other color. So let's go to like a blue. That way we can see them on our oscilloscope as different values. When we double-click on this, it gives us a window here, and we can hit play and see very little at first, right? They're both just on this white line. And technically we can separate them if we wanted to separate them. We can see that both of them are at 0, right? So we move that back up there. As soon as we flip our switch a couple of times, we'll see that there's something that starts to happen here. So we'll do it a couple times, we'll pause it, and we'll zoom in a little bit here, and we'll see that at the top and bottom, let's move this red signal back down out of the way, and zoom in using our time constant. At the top and bottom of our signal, we're seeing there's this tiny little peak, and then a tiny little peak at the bottom of the red signal too. And the tiny peak across the blue one at the rising edge is the inductor pushing back, and then the tiny little signal at the bottom of the red is the inductor pushing back also, and we're going to call that flyback voltage. Right now it's really, really small because our inductor is really, really small, but inductors can also be motors. So when you look at a motor, it's an inductor. Right? And so we need to be cautious because those inductors are much, much larger than this inductor, and it's going to have a much larger peak output when you send a new current through there. And so we got to protect against that. That's why we put diodes around our motors. And that's also why we have capacitors around our motors so that we don't end up accidentally overshooting that spike that comes out when we send a new fluctuating current through the signal. Okay. So we're going to leave our oscilloscope there, but we're going to replace our switches because I can't switch it fast enough to make up for the nanoseconds that we need. And so we're going to delete these two out. We're going to replace that with a function generator. So the function generator is the second one on the right-hand sidebar there, or you can go to Simulate, Instrument, and the second one there also is function generator. And this is going to be like the audio of a microphone, that kind of thing that we're going to send through this filter. So it's going to simulate that for us. I like to right click on this and flip it horizontally so that my positive terminal is next to my resistor here. That way I can easily connect it back in there. And we see that this blue wire, or this A terminal here, is still connecting to the positive of our source here, so that's still good, and it has ground on the other side, so that's still going to read the same thing. It's going to read our source and compare it to the resistor R1. Then our ground goes to common. It does not go to the negative terminal, and if you do put it on the negative terminal, it will not work. We're going to use that negative terminal for something else later, so remember that ground goes to common. Okay, so now we need to set up our function generator. We'll double click on that. We want it to act like the switch that we just had, so we're going to set it to this oscillating DC square wave, and we want to set it to a higher frequency. We need it really high. We need it like 50 kilohertz. Watch out for your frequency. They gave you a frequency to set it to. My amplitude here is 10 peak, right? It's not peak to peak. So watch out for that too. If they give you something to set into your function generator and it's an RMS, switch it to peak. If it's in peak to peak, switch it to peak. Put it in here as a peak voltage only. So that means that our peak to peak is actually 20, right? Because our peak is 10, it goes 10 rising to the top, negative 10 to the bottom. So that gives us a total of 20. So when we double click on this, here's our old signal that we had. Let's re-zero out our red line there, and then when we hit play, we should see our new signal. It's much, much smaller, really, really fast, right? That's what we wanted. So we're going to take our time base down here. Let me zoom this up here. Down here at the bottom, and we are going to scale it down until we actually see our signal. We're going to make it zoom in on our signal more and more and more, and we start to see it there, but we're going to keep going until we get a nice, clean, and clear signal across our screen here. Go up one there. So 5 microseconds gave me a clear signal. Yours might be different depending on your frequency. So I'm going to pause it there. I'm going to scroll my thing back here. We might go in one more here. That way we can see this slope. And that's what we're going to be calculating into. So I'm going to center that. That's what we want to look at, is this one signal. We see that we have a slope at the top. We have a slope at the bottom. It's really small because our inductor is really small and we got a really large resistor. Right? So it's going to change that time constant. It's going to be a really fast time constant. And so we're going to calculate some of these values. We have 2 probe lines over here. We have a channel 2 probe and we have a channel 1 probe. And you can drag them out. We know that channel 1 is going to be T1. It comes across here. You can move it using these 2 arrows here as well. You have a time constant for channel 1, so anytime you move channel 1, you'll see that that time constant is eventually going to scale up and down. And we know that 0 happens at the left side of our oscilloscope. That's 0 time, and it scales all the way up to however much time that we use it for, however long we run our oscilloscope for. After that, we have channel A is at negative 10 volts on T1, and we see that that's down here on the bottom, right? So it's reading the red line at the very bottom, and we actually don't see the red line because the blue line's blocking it, right? But it is under there. We see it only when the blue line gets off of the red line. After that, we also have channel B's voltage at that same probe line. So T2 measures both the voltage for channel A and B at that exact time interval. And so right now they match at the bottom there. And at the top here on channel 2, we see they match as well. We got 10 and 10 for T2, and their time factor is shared. So at this time factor, channel probe line here, 2, is reading 10 on both of our 2 channels that we have. T2 minus T1, this last one here, is going to give us the difference between our 2 probe lines. Right, so this blue one here is at a specific factor, and if I move it further away, we end up getting a higher time value here. And if I move it closer to my yellow one, we end up getting a really small time value here, and that's what we want to compare. This second one here is comparing the voltage on both of those. Since both of those both say 10 volts right now, it's 0, right? 10 minus 10 is 0. But if I were to move this one back down to that negative terminal, negative 10 minus positive 10 is going to be 20, right? That's going to be a 20 peak to peak. And we see the same thing for this other one, but when we get into that sloped region, we see that this other side changes. It follows that blue line, and we end up getting a slightly different magnitude down here. And so we want to evaluate that, specifically the slope on this line here. And we can continue to zoom in. If you wanted to get closer to that and see exactly where that slope is landing, you can zoom in, because that's really all we're really focused on right now is this rise time, right? That's our time constant, is how fast did this signal rise. And that depends on a lot of things. It depends on our peak voltage for the circuit, our peak to peak voltage for the circuit, and also this chart that I have at the top right here. That's our time constant chart. We have 5 time constants, and that basically says that on average, it takes us amount of percentage to get to the top of our signal. So after the first time constant, we expect to be about 63% of the way to our total current for the circuit. And then second time constant is about 86.5% of the way. Right? So it's rising quickly. At third time constant, we're 95%. At the fourth time constant, we're 98.2%. Right? And at the fifth time constant, we're considered to be 100% there. And so that is what we're talking about with time constants, and that is what we just calculated. 68.2 nanoseconds should be each of our stages for our time constant. And so we're going to measure those out. We're going to see where exactly those fall on this blue line versus the red line. So our first measurement that we need to take here is moving this all the way to the very beginning of our signal generation here. And so that's right there at that top one. And again, you can move these using your little probe lines here if you wanted to move them back and forth like that as well. That works. Right? And just note the time difference. So if you're really, really close to what you expected it to be at, then you can move back 1 or 2 and you'll see that that is going to fix that for you. Okay, so we're going to keep it right there at the very bottom of this blue line. And then this other one, we're going to click on it first, and then we can drag it forward. And we want to actually make our time constant, right? So we actually don't know what this 19.93 volts is going to be at our first time constant. We just know how long that time constant is. And so to find this number, we need to figure out what that voltage is supposed to be. Right? And so we can do that. We can say that we have a peak voltage of 20 in my circuit here, because that's 10 times 2. That gives us peak to peak. And we can multiply that by our first time constant, which is 63.2%. So what is 63.2% of 20? So we'll multiply that. We did that by 0.632. That's our percentage, right? We're going to move it into that decimal range for calculating percentage. And we're left with 12.64. So that is our voltage at that location, 12.64 volts. And that is our first time constant. Right? Our first time constant should be 12.64 volts. What does that mean? So when we look at our signal here, we'll see that we have this white line in the middle, and that's 0 volts. Below that is negative voltage, and we know that it goes to negative 10. You see that right here on our channel B, goes all the way down to negative 10. And so we want to say, well, we're going from negative 10 up to 0, and then up to a positive 10 after that. And we want to account for that in this number here when we're writing it into our oscilloscope. So that means that we can take the negative that we know we had at the bottom. Let's send this out. We'll say we have negative 10, and we actually want to get up to 12.64 total magnitude rise, which means that on the positive side of our signal here, we should be at about 2.64 volts. So currently we're not following our blue line. So to do that, you want to double click on your blue line. It's kind of hard to do, but to try and double click on your blue line there, you can also right click and switch your trace, select trace, and that's going to give you the option to choose channel A or B there. We're going to channel B. Okay, that. And so now we're following. You see that yellow circle is following that blue line now. And that makes it nice for us because we can send it all the way back here, right click it, and tell it to go set Y value backwards to whatever value I tell you to. Right now it's at 10, and we want to set it to 2.64. 2.64. Well, okay, that. And so it jumped over to 2.64 volts backwards. And we see that that gave us 12.64 down here, and that's exactly what we measured our voltage at, or calculated our voltage at for our time constant. And then we also see something else over here. We got 78.898 nanoseconds. And if we move T1 over just one click, we got 69.428. And we see that T1 actually lined up perfectly on that line right there. And so that's probably going to be as close as we're going to get to our time constant as we measure it. These are not perfect circuits, but they're going to get pretty darn close. So that means that we verified it. This right here is our time constant, right? That's the distance between the beginning of our circuit and our very first time constant. So if you were to take the blue wire or the blue probe line and move it to your next time constant to find the voltage for that one, the same way we did this last one, taking your percentage of 86.5, multiplying it by your peak voltage, that would give you your next value. And then you should see that the distance between your second time constant and your first time constant is also 68.2 nanoseconds. This is really important when we're trying to pick filters. Okay, let me know if you have any other questions.